Questions 5 through 7 on the 2010 grade 12 Euclid Math Contest. If f at x is equal to 2x plus 1 and g at f at x is equal to 4x squared plus 1, determine an expression for g at x. F at x is equal to 2x plus 1. Now they are figuring out something interesting, g at f at x. And they have actually given us what that is equal to. It's equal to 4x squared plus 1. So our task is to figure out what is g at x, and it's going to be some polynomial, obviously a quadratic, of the form ax squared plus bx plus c. And we, of course, have to figure out these coefficients a, b, and c. So let's start with what they've given us, and that is g at f at x. Well, f at x is 2x plus 1, and that's equal to 4x squared plus 1. So I will substitute them into that form. So a times 2x plus 1 all squared plus b times 2x plus 1 plus c, and that is equal to 4x squared plus 1. So obviously I've got to expand this all out. So we've got 4ax squared plus 4ax plus a, and then this one will just be 2bx plus b, and then we just got a c. And now I think we can compare the coefficients. So let me just factor them first to make this look identical, or as close as I can. So I've got 4a and then x squared. And then the coefficient in front of x is 4a plus 2b. And then everything else is sort of just all by itself. And that's 4x squared plus 1. Okay, so this is equal to 4. This is equal to 0 since there is no x on the other side. And this is equal to 1. So those are the equations. The first one, 4a is equal to 4. So immediately we can figure out that a is 1. That's very good. The next one is 4a plus 2b is equal to 0 because the other side has no x term. Now a is 1, so that means this is 4 plus 2b is equal to 0, and therefore b is equal to negative 2. And then finally, this guy right here is equal to 1. So a plus b plus c is equal to 1. A is 1. B we just figured out was negative 2. So that means c is going to be equal to 2. So we've got our three variables, our three coefficients. So g at x therefore is a, which is 1, x squared. B is negative 2, x plus c, which is 2. And that's it. X squared minus 2x plus 2. And I encourage you, as always, to verify. Put in 2x plus 1 into this, expand it out, and if you do, you should get 4x squared plus 1 when you collect like terms. A geometric sequence has 20 terms. The sum of its first two terms is 40, sum of its first three terms is 76, the sum of its first four terms is 130. Determine how many of the terms in the sequence are integers. A geometric sequence is a sequence in which each term after the first is obtained from the previous term by multiplying it by a constant. For example, 3, 6, 12 is a geometric sequence with 3 terms. So we have AR squared, AR to the third, and so on. These are the terms of a geometric sequence. They're just multiplying by r each time. And they tell me that the first two add up to 40. So A plus AR is equal to 40. And the second sentence here tells me that A plus AR plus AR squared, if you add those, it equals 76. And if you add the first 4 terms, it equals 130. So these are our three equations, and this is what we have to work with. So from the first one, I can deduce that a plus ar is 40, so I can factor out the a, and that gives me 1 plus r is 40. So I can isolate for a, that's going to be 40 over 1 plus r. And there's many ways of doing this. I just did it this way because it's most comfortable for me. Now the second equation, from that one, I get that a plus ar plus ar squared is equal to 76. Now if I factor out an a here, I will get a times 1 plus r squared is equal to 76. And a is 40 over 1 plus r. And I've got 1 over 1 plus r squared. Cross multiply and then expand, you get 40 plus 40r plus r squared is equal to 76 plus 76r. Now let's collect like terms. If I do, I get 40r squared minus 36r minus 36 is equal to 0. And obviously I can divide through by 4, so then I'll have 10r squared minus 9r minus 9 is equal to 0. I don't think this factors very nicely, so I can just use a quadratic, and that shouldn't be a big deal. R is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So therefore r is going to be 9 plus or minus 81 plus 360, the square root of that, all over 20. And looks like r is going to be 9 plus or minus, that it becomes 21. And therefore this is going to be 30 over 20 and negative 12 over 20. And in lowest terms, that's 3 over 2 and minus 3 over 5. So we're doing the most complete solution possible for this question. Okay, so let's figure this out now. Let's first just concentrate on the first 4 terms, and then we will extrapolate to all the 20. If r is 3 over 2, let's talk about that one first. My first 4 terms, a, I can substitute r into that and get a. So that means a will be 40 over 1 plus 3 over 2. And if you do that math, you get 16. So my first term is 16. Second term is ar, so it's 16 times r, and that will give me 24. And then very similarly, the third term is ar squared, 16 times 3 over 2 squared, and that is 36. And the fourth term is ar cubed, which is 16 times 3 over 2 to the power of 3, which is 54. So those are my first 4 terms. Now, before I proceed, let's see if this checks out. Our rules are as follows, that the first 2 terms have to add up to 40. And they do. 16 plus 24 is indeed 40. So that's good right there. The next 3, the 3 terms have to add up to 76. 16 plus 24 plus 36 is indeed 76. And then all 4 have to add up to 130. And they do. It becomes 130. So that means that when r is 3 over 2, this works out beautifully. Now we have to, of course, verify the next one, which is minus 3 over 5. And that one I'll just do real quick. If r is equal to minus 3 over 5, we actually get the following for a, ar, and ar squared, and ar to the power of 3. You get 100 minus 60, 36, and minus 21.6. And these numbers, interestingly, do not fulfill this criteria. So we can just reject that value of r. So we are only interested in r equals 3 over 2. So if r equals 3 over 2, let's proceed and figure out a1 through a20. And the good news is that we can easily figure these out pretty quickly. The first few we already did. They were 16, 24, 36, and 54, right? And each of these, of course, is AR squared, AR to the power 3, and so on. AR fourth, AR 5, and so on, right? So if you have a calculator, and calculators are allowed, you can easily just do that. You can just put in put in r equals 3 over 2, and then just keep multiplying by 3 over 2, and you'll get each of these. And if you do, you'll get 81. But then you start getting values with decimals, 121.5, 182.2, and so on. So I'll write them all in. So as you can see, when you do them all, the only ones that end up becoming integers are the first 5. And then after that, you get all these decimal values. And that's what they're asking. How many of the first 20 terms are going to be integers? Well, it's just 1, 2, 3, 4, 5. So 5 integer values. And that's it. That's what they're asking for. And the answer, of course, is 5. A snail's shell is formed from 6 triangular sections as shown. Each triangle has interior angles of 30, 60, 90. If AB has a length of 1, what is the length of AH in centimeters? This question, of course, at the heart is the 30, 60, 90 triangle. And in any 30, 60, 90 triangle, for example, this first one, the ratio of the sides are always going to be as follows. 1 for the side opposite 30, 2 for the side that's opposite the 90, and root 3 for the side that is opposite the 60. That is the ratio of the sides. So what we're going to do in this question is label each of these, and we can calculate each hypotenuse with these ratios. So for example, and this will become a repetitive pattern, you'll see the very first one, which is AC over AB. If you just use the 30, 60, 90 ratios, you will see that AC over AB, where this is AC and this is AB, is equal to 2 over root 3. That is the ratio. But AC can be calculated in terms of an actual value because AB is 1. So if you cross multiply, this just becomes 1 times 2 over root 3, and therefore AC is just 2 over root 3. So we got the first one, AC. Now we will do the exact same thing to figure out AD. Again, if you look at this triangle, ADC, it's the same story. It's again a 30, 60, 90 triangle, and therefore the sides have the same ratios. AD over AC, again, is 2 over root 3. So cross multiplying, AC we know is 2 over root 3. So 2 over root 3 for AC multiplied by this 2 over root 3 is going to be my value for AD, and that is 4 over 3. All right, so I hope you get the hang of this. So we just have to keep doing this over and over again. So we just got AD. Now I have to do AE. Okay, again, AE over AD is equal to 2 over root 3. Therefore, AE will be AD times 2 over root 3, and AD is 4 over 3, times 2 over root 3. So this is equal to 8 over 3 root 3. Okay, so let's just keep going. We just got AE. Now we have to get AF. AF over AE is equal to, again, 2 over root 3 So AF will be equal to AE, which is 8 times 3 root 3 times 2 over root 3. And this is 16 times 3, which is 9. So that takes care of AF. And now we have to go with AG. AG over AF is equal to, again, 2 over root 3. So that means AG is equal to 16 over 9 times 2 over root 3. So that is 32 over 9 root 3. And finally, now that we have AG, we can finally calculate AH. AH over AG is 2 over root 3. So AH is AG, which is 32 times 9 root 3 times 2 root 3. And that is 64 over 3 times 9, which is 27. 64 over 27 is the value for AH. In rectangle ABCD, point E is on the side DC. Line segments AE and BD are perpendicular and intersect at F. AF is 4, DF is 2. Determine the area of quadrilateral BCEF. To figure out that area, I'm going to break up that quadrilateral into two triangles by joining E to B. Once I do that, I can figure this out. This is, of course, a right angle since it's a part of a rectangle, and this is a right angle also. So it's two right triangles, and we can figure out the area, therefore, as follows. That quadrilateral BCEF will really just be the triangle BEF plus the triangle BEC, or BCE. So that will be 1/2 base times height. For BEF, it's EF times FB. And then for triangle BCE, it's EC times BC. So I have to figure out each of those to figure out this area. Well, let's label the only thing they give us, that AF is 4 and DF is 2. Now, since this is a right angle, I can quickly figure out AD with Pythagoras. AD squared is 4 squared plus 2 squared, which is 16 plus 4, and therefore AD is root 20. And root 20, if you want, you can write it as 2 root 5. So that means this is 2 root 5 right here. Now, it's a rectangle, so that means BC is 2 root 5. So in this equation, I've got 4 things I have to figure out, and one of them I just quickly figured out, which was BC. It's 2 root 5. Okay, so where do we go next? To get further values, now I have to look at similar triangles, and I'll explain what I mean. If I label this angle here as theta, then since this is a right angle, this one here is 90 minus theta, that angle. And this angle is also 90 minus theta, since these two have to add up to 90. And therefore this angle will be theta, since this is a right angle. And in a very similar way, this is also a right angle. It's all right angles. And this is 90 minus theta, and this angle is theta. So as you can see, you've got 3 triangles that are similar because they share the same angles. So we can first talk about ABF, that triangle, being similar to triangle ADF. And in particular, the sides AB over AF are the same in this ADF to DF. So just in case you're not familiar with similar triangles, AB is the side that has theta and 90 minus theta. And AD on this triangle is also the side that has theta and 90 minus theta. AF is on this triangle the side that has theta and 90, and DF on this triangle also has the same angles, theta and 90. So that's how you do that comparison. Well, AB therefore will be equal to AF if you cross multiply, and AF is just 4. AD is 2 root 5, and DF is 2. So this becomes 4 root 5. So let's put that in there, 4 root 5. Okay, so now I think we can get this side pretty quickly with just Pythagoras. So that's going to be just AF squared plus BF squared is equal to AB squared. AF is 4, so that's 16, plus BF squared. AB is 4 root 5. So if you square it, you get 16 times 5, which is 80. So therefore, BF squared is 64, and therefore BF is equal to 8. So I've got another piece of the puzzle. This is 8 right there. Now we can continue using similar triangles. In particular, triangle DEF is similar to triangle ADF. And from that, you get the following relationship, that FE over FD is similar to FD over FA. And plugging in our values, you get FE is equal to over 2 is equal to 2 over 4. And solving for FE, you get FE is equal to 1. So FE or EF is 1. So there you go. I've got one more value, and that's EC. EC is from here to here. Well, to get EC, what I can do is I can first figure out the entire length, which is DC. So, and then from that, I can subtract DE. Now the good news is DC is the same as AB, so DC is 4 root 5. So if I can get DE, then I'll be able to get EC, and then I'm done. Okay, so DE, how do I get that? Well, DE I'll get with similar triangles, in the very same way, triangle DEF and triangle ADF. Those should be enough. So I got DE over FD is equal to AD over AF. And that is DE over 2 is equal to 2 root 5 over 4. So solving for DE, you get DE is equal to root 5. So put that in here, root 5, and therefore EC is 4 root 5 minus root 5 is 3 root 5. So there you go. This is 3 root 5. And that's it. And now I just got to do this math here to figure out the area of BCEF. This is going to be 4. I think I can squeeze it in. And that, if you multiply it all out, is 5 times 3, which is 15. And therefore that is 19 for the area of quadrilateral BCEF. Determine all real values of x for which 3 to the power of x minus 1 times 9 to the power of 3 over 2x squared is equal to 27. 3 to the power of x minus 1 and 9 to the power of 3 over 2x squared is equal to 27. So obviously we've got to get everything in terms of 3. This is already in terms of 3. Make this 3 squared, and that is going to be 3 to the power of 2x squared. And 27, of course, is 3 to the power of 3. So this now becomes x minus 1, and then this is 3 to the 3 over x squared, because those 2's cancel when you multiply. And that's 3 to the power of 3. Combining, you get 3 is x minus 1 plus 3 over x squared is equal to 3 to the power of 3. Since the bases are the same, the exponents are the same, so that means x minus 1 plus 3 over x squared is equal to 3. So that takes care of the first part of the question. Now, multiply through by x squared and collect like terms. And if you do that, you get x to the power 3 minus x squared plus 3 is equal to 3x squared. Putting everything on one side, you get x to the power 3 minus 4x squared plus 3 is equal to 0. So we have to find solutions of this. Unfortunately, there's an x to the power of 3. Okay, shouldn't be too much of a problem. By inspection, I can quickly see that 1 is a solution. If you substitute 1, you'll see that it works. So x equals 1. That is a solution. So that helps me because I can now factor this. And when I factor, some of you can do it without having to put in a new polynomial. But just for the sake of completeness, I'll do it in a way that can be explained fully. So it's x minus 1. That is one of the factors, since x equals 1 is a solution. But the other polynomial, or quadratic, is going to be ax squared plus bx plus c. And when you multiply it out, the total product will be x to the power 3 minus 4x squared plus 3. So when you expand this out, you get ax to the power 3 plus bx plus xc minus ax squared minus bx minus c. And that is equal to, of course, x to the power 3 minus 4x squared plus 3. Now what we have to do is compare coefficients. Let's just make it in that form as closely as possible by collecting like terms. And if you do, you get ax to the power 3, b minus ax squared plus c minus bx minus c is equal to x to the power 3 minus 4x squared plus 3. Now that means that this a is the same as 1. So immediately we get a is equal to 1. And then b minus a is equal to negative 4. Well, a is 1, so that means b is equal to negative 3. And this minus c is the same as 3, so that means minus c is 3, so that means c is negative 3. So going back here, we can substitute that in, and that means this is x minus 1, x squared minus 3x minus 3. That is the factors of this polynomial. But how do I get the roots there? Well, obviously I have to set that equal to 0. And that's going to involve a quadratic, no problem. Minus b plus or minus the square root of b squared minus 4ac, like that, all over 2a. And therefore x is equal to 3 plus or minus, this is 9 plus 12 is equal to all over 2. So this is 3 plus or minus root 21 over 2. So there you go. Those are my roots. X equals 1, x equals 3 plus root 21 over 2, and x equals 3 minus root 21 over 2. Determine all points x, y, where the two curves y is equal to the log of x to the power of 4 to the base 10, and y is equal to log of x to the base 10 all cubed, intersect. To make matters simple in this question, I will let log of x to the base 10 equal some variable. We can just call it a. So this equation, when we set them equal to each other, obviously that's how you find the intersection points. The first one is, of course, log x to the 4 to the base 10, and the other one is log of x to the base 10 all cubed. Using log rules, the 4 comes out front, and then you just get log of x to the base 10, and this is essentially the same. Now, we can make our substitution. So a is equal to log of x to the base 10. So this becomes 4a, and this becomes a to the power of 3. Putting everything on one side, you get a to the power of 3 minus 4a is 0. Factoring out an a, you get a squared minus 4 times a is equal to 0. So that means that a is either equal to 0 or a squared minus 4 is equal to 0. If a squared minus 4 is equal to 0, a squared is equal to 4, and therefore a is equal to plus 2 or minus 2. So these are our three values of a. Now we have to figure out x and y because they want the points x, y. Okay, so we'll do this one step at a time. First, let's start with a equals 0. If a is equal to 0, that means that the log of x to the base 10 is 0, and therefore 10 to the power of 0 is x, and therefore x is equal to 1. If x is 1, we can use any of these equations, either of those equations, to figure out y. If I just substituted in the first one, it becomes the log of 1 to base 10, and therefore y is equal to 0. So my first order pair, x, y, I'll just list them here, is 1, 0. Now let's look at a equals 2. If a equals 2, that means the log of x to the base 10 is 2, and that means 10 to the power of 2 is x, and therefore x is 100. If x is 100, we plug that into any of the y's. We get y is equal to the log of 100 to the power of 4 is to the base 10. And this is, of course, just log of 10 to the 10 squared to the 4, which is log of 10 to the power of 8 to the base 10, and that is just 8. So there is our second ordered pair, and that is when x is 100, y is equal to 8. We got one more. I think I can squeeze it in anywhere. I'll just do it over here. And that final one is when a is minus 2. When a is minus 2, we have log of x to the base 10 is minus 2. So 10 to the minus 2 is equal to x, and therefore x is equal to 1 over 100. If x is 1 over 100, we substitute into the y equation. You get y is equal to, that's 10 to the minus 2. So 10 to the minus 2 to the power of 4, log to the base 10, and that becomes log of 10 to the minus 8 to the 10, and that is just minus 8. So our third and final ordered pair, x is 1 over 100, and y is minus 8. So those are our 3 points that satisfy the fact of these curves intersecting. So they intersect when x and y are these 3 points.